Okay, so this video will be somewhat dense because we'll talk a lot about the math behind support vector machine, but hopefully it will be easy to understand. So let's get back to our example. Let's just remove the extra things. So by now we know that this is the decision boundary, the dotted street is the decision boundary, and these points are the most important one. We need to maximize the distance. Sorry about that. So we need to maximize the distance between these closest points to the boundary and the boundary itself, right? So let's say we have instead of tall and weight, we have these values are negative and these values are positive. Just for explanation. Oops. So these values are positive. So we know that we have a decision boundary, but we need a decision rule that would use that decision boundary, right? So let's say we have a vector W here, and that vector W, sorry for the color, I need to change the color. Okay, so let's say we have a vector W here, and that vector W is orthogonal. Yeah, this vector W is orthogonal to the decision boundary. And then we have but we don't know the most important property here. We don't know the length of vector W. Then we have an unknown point called U, and we have a vector that points to it, right? So what is important here is we need to know which category this unknown points belong to, right? But first we need to project that unknown point. So we need to project that unknown point here to project it to W. So why is that? We need so it would be also orthogonal to the street or the decision boundary. So we take so what's the mathematical equation will be? So we take W dotted with U, with the dot product with U, dotted with U, and then we need to know if the projection is greater or equal to some constants, some constant C, right? So if this projection is above C, it will be if this dot product is above C, it will be in this side, and it's below C, it will be in this side. So in general, we can say that so from this equation we can say that W dotted with U plus some constant B dotted with U plus some constant B greater or less than 0. So let's say this is our first this is the decision rule. But here we have a problem, right? Because this we don't have either W. Let's change the color. Let's say so we don't have W and we don't have B. So how can we use that? Because we don't know either W or B, we need some constraint that will tell us what W and B is. Something like, which is the same concept of linear programming, right? Because we have this function, and we need some constraint to know W and B. But so why we don't know W or B? Mainly because as we know W, we don't know any the length of W, and there's a lot of vectors that are orthogonal to the decision boundary, right? So we need some kind of constraint. So what is the constraint? The constraint, we introduce a value of y. What is this value? So we need to value of y sub of I. This value y of sub of I such that when y sub of I equals to +1, then it will be for the plus samples. And if y of I equals to -1, it will be for the minus samples. And when we apply value y to the decision rule, we have the constraint. We get this constraint y sub of I to x sub of I dotted with w plus b, which is these are vectors, dotted with b -1 equals to 0. So this is the decision rule. This is the constraint. Okay. So our goal is to make the margin or the street. So let's get back to our example, right? Let's just remove this. Okay, can remove this, and this. Okay. So our goal is to make the margin as wide as possible. That's the goal, the whole goal of support vector machine. But first we need to measure the distance between the goals, right? So let's say we have so we need the distance of this margin. So let's say we have the same example. Okay, let's say we have another vector that is pointed to this point, which is, let's say this is x plus, and then we have a vector pointed to this example at this point, and this is x minus. But so we need the width of the street, right? So we need this this distance. How can we get this? If we get this one is the width of this is the difference between x plus minus x minus. And if we dot these values to the normal vector w, we get the vector of the width of the street. So so let's say x plus minus x minus dotted with w. That will be dotted with w with the magnitude of w. That will be equals to width of the street, right? So but these values, so we use the constraint, this constraint to get the values of x plus and x minus, because now we know that x plus equals to it will be positive, and x minus it will be negative. So that so we just, this value will be 1 minus b when we apply, okay, when we apply x plus to this or x minus to this, we will get 1 minus b for x plus and 1 plus b for x minus. And this will be equals to, as this is our constants, we will get 2 of the magnitude of w. So this is the value that we need to maximize. But for mathematical convenience, we need to get it as max. So we need, this is the max. So we need to maximize to the magnitude of w, and then we can transform this to minimize the magnitude of w, and then that will be, it will be transferred as well to minimize half magnitude of w to the power of 2. And this So we know why we did this step and this step, but this step is just for mathematical convenience. So now we have, this is what we need the extremum of. So we need to maximize this, which means that if we maximize this value, we maximize the width of the street. So the whole equation will be, we need to maximize this by as well as honoring this constraint. We solve this by the Lagrangian formulation. We need the extremum of this value by honoring as well as honoring this constraint, and this is solved by using the Lagrangian formulation. Sorry for the pronunciation, but that's the name of the formulation. Okay, so let's start by, when we apply these values to that formulation, we say L, which is the formulation. Then we have half of magnitude of W to the power of 2 minus the sum of alpha I, and then the constraint. We have W dotted with x of I plus b minus 1. So then we need to differentiate L to W. When we differentiate, we get W minus the sum of alpha I, the sum of alpha I y of I, and then x sub of I equals to 0, which this equals to, we get W, and this is a vector of W, then we get W equals to the sum, okay, I'm really bad at drawing this, but the sum of alpha I y of I and x of I. So we get a partial value of W. Then when we differentiate L to the constant b, we get the sum of alpha I y of I equals to 0. So that will be also beneficial for us to calculate what is the function that we need to maximize. So then when we apply, so we get these two values. When we apply this value, okay, when we apply the value W to this and this, so now we have a value of W, then we just apply W to the formulation we got from the Lagrangian formulation. So we get L equals to half of sum of alpha I y sub of I x of I, that is this, then this is dotted with the sum of alpha j y of j and then x of j. This is, and then we take it from the sum of y of I, alpha of I, then y of I, x of I, this is I, dotted with the sum of alpha j y of j x of j, right? Yeah. Then that will be, and then we get from alpha I y of I b plus the sum of alpha I. So we get this formulation, right? So how can we solve it? So this is, we know this b is constant, right? If we move this b here, this value is, we get this value is equal, this value are this value, right? So which is 0. Then, and now we get this. So these two expressions are the same. So half minus this expression will be half minus this expression will be L equals to the sum of alpha I, which is this one. Then we got minus half the sum of I, sum of I, the sum of j alpha I, alpha j, y of I, y of j, x of I, x of j. So basically this what we need to get the extremum of. So that's so why did we actually do this in the first place, right? So we did, okay, this I can't actually, my handwriting is really bad, I can't differentiate x from y. Okay, let's say this is x, y. Okay, so why we did this in the first place? So now when we do this formulation, we know that so this is the dot product, right? So we know that all of this, the maximization of the width of the street, are depending on the dot product of the two vectors. So that's the most important decision, the most important point we take from this calculation. Then, so we have a value of w, we have this expression, we have this formulation. And then we have the decision rule here. So let's apply w. We get this w to the decision rule. When we apply, so it's basically, if we need to, I just basically this to this. So when we apply w to the decision rule, we get the sum of alpha I, y of I, x of I, x of I, dotted with u, which is the unknown, plus b, which is bigger than to 0, greater than or equals to 0, then we know it's positive. So we know that now the decision rule depends on the dot product of the simple vectors and the unknown, which is this. We know that the decision rule is depending on the sample values dotted with the unknown vector. So now let's do like what happens when we get data that are not linearly separable. So let's get to this example. So we have, like, let's say this example, like what is the right time to eat a banana. Like I did at like the first days here, the first days it will be so green that it will be not tasty, but there's like a perfect time to eat the banana here, and then it will be not good because it will be it will rotten or something like that. So this is not it will be too long to eat the banana. So how can we separate this? We can't get a threshold here because we didn't separate between the two, or here or here. So this is not wrong and wrong. What SVM do when we have data that's not linearly separable? We do a transformation. What is that transformation? So the transformation map the data to a higher dimension. So this data is one dimension. We transform the data to 2 dimensions. So we do a transformation on the data that took us from 1 dimension to another dimension that are more convenient for us. So let's say now from one dimension to 2 dimensions. Let's say this the old data, then we took the power of 2 of these values, then we get a slope, then we can linearly separate the values. So then we get like something like this, right? So phi is the transformation that happens to the data, but most importantly, we know that the maximum of that rule, it depends on the dot product, which is, we got it from here and here, right? So we know that the maximum is depends on the dot product. So the transformation will be the transformation will be, let's say this, we have xi, then this is dot product of that transformation of xj. So now we are getting somewhere. So now we need the max. So now we get that transformation of the unknown, right? So we have x of I dotted with that transformation of x of u. This is what we need. This is exactly what we need, and it's just what we need to know what's the value of u. So let's say we have a function k that takes x of I and x of j, which is transform x of I dotted with transformation of x of j. So what does that mean? So this is what we need to know, a function k, to know that to know what happens to the dot product. So we don't actually need to know what the transformation that happens in another space. So this is like the this is the whole deal of SVM, that even like if we have another dimensions like 3, 4, I don't know how to draw more than dimension than that. We don't need to actually know what happens in the other dimension, that transformation that happens in another dimension. We just need to know the function, which is the kernel. And that's why I think Professor Patrick Winston called it a miracle, because if you think about it, it actually is, because like we don't actually need to know what's the transformation that happens in the dimension 3, or if we have a 5 dimensions data that have 5 features, you don't need to know what happens in the when you transform the data to 10-dimensional or something like that. So lastly, let's look at some examples of the some kernels. So we have a polynomial kernel, which say that x of I plus dotted with x of j plus 1 to the power of d. D is the degree of that polynomial. Then we have another kernel, which is the radial basis kernel, which is e minus the magnitude of xi minus xj. Then we have sigma. But here, when we have this kernel, we have a problem that when we have a small enough sigma, a small enough value of sigma, we then the data is shrunk right around the data points, which we get a problem of overfitting, which is a problem that happens in support vector machines, but at least it will avoid local minima or local maxima that neural nets struggle with. So let's draw what we mean by the radial basis function. So let's say we have data points here in the middle. These are the red ones, and then the blue ones are just circling them. Right. And we can just do like this, here. Okay, So now, how can, this is like not linearly separable, right? So the SVM transform this data to like 3-dimension. Well, like if eventually it will be something like this. If we have a third one here, so the red ones will be something like this, and then the circled ones will be in depth like there. If that makes any sense, if you can imagine it. So then, but if you want to draw it in 2D, literally the SVM, the kernel function, the radial basis function will take. So the values are we want to maximize the distances. These ones are these. So this, and these ones, right? Well, so then. Let me just remove that. So the decision boundary on the hyperplane will be something like this. So the kernel function will draw a hyperplane like this, and then the street will be around all the points. My drawing is not perfect, but it gets the job done. So that's basically the decision boundary that happens with the kernel basis function. That's the basic idea of support vector machines, and why is it a miracle? What's like a famous professor in computer science called it. So the most important point, if you just, it took me a while to understand the math, I'll be honest with you, but when you understand it, it will just click in your head what exactly happened. But if you just get you an overview, is that the basic idea of SVMs is that support vector machine is that if we need to maximize, so the goal is to maximize the width between the decision boundary and the closest data points. But if we have a data that is not linearly separable, it is not easy to separate them, we transform it using some kind of function called a kernel. But the most important in that kernel that you don't have to get what actually happens in the transformation itself, because it depends on the dot product, which we get from these math equations. So yeah, that's about it. I hope you enjoyed this model, and I'll see you next time. Thank you.